Let's talk briefly about rate laws. This can be a challenging concept, but once you get the hang of it, it goes pretty quickly. What you're looking at is seeing how the concentration, expressed as molarity, moles per liter of solution, moles of solute per liter of solution, how that changes, so the change in molarity, how that changes as a function of time. Now you can measure reactants disappearing, or you can measure products appearing. You do something called spectrophotometry. You don't have to worry too much about that, but when you get to AP, you actually get to do it. Imagine a reaction vessel here. You've got light of some intensity, some initial intensity, and your reaction is taking place in this vessel. Now, reactants are going to be disappearing and products are going to be appearing. So let's say as product forms, this light is tuned, it has a particular wavelength or frequency to this particular product. The more product I form, the lower the intensity of the light that would leave the vessel. And if I vary the concentration of my reactants, I'll vary the concentration of my products. I can see how quickly the reactants get used up or how quickly the products appear. This is something you'll actually get to do during AP class. It's not as important to understand the ins and outs of that as it is to understand the way to manipulate the data. Basically, you do a series of experiments. You change concentration of the reactants. And you measure the rate of appearance or disappearance to see how the concentration of the reactants affects the rate. Now, let's just say we had a system A was turning into B. And in experiment number 1, the concentration of A, let's just say it was 0.1 molar. And the rate of appearance of B was, we'll just say 10. We'll worry about the units later. Let's double that concentration. Hey, the rate stayed 10. There was no effect. If there's no effect, if I was measuring the rate of reaction as a function of the concentration of A and it stayed flat, no change, we would call that zero order. Okay, zero order, anything to the zero power has no effect. So zero order would be a flat line. Okay. What if, though, if I doubled A and the rate doubled? If I measured the rate as a function of the concentration of A, and every time I doubled A, the rate doubled, I'd get a first order linear directly proportional relation. Okay, first order is a straight line with a positive slope. What if I doubled the concentration of A and my rate went from 10 to 40? I doubled A and my rate was 4 times faster. Isn't that 2 squared? I would say that this would be a second order expression. If I was looking at my rate as a function of the concentration of A, what I'd see is half of a parabola, an exponential function. Okay, so how does that work? Whenever we have a system, let's just say we have A plus B goes to C plus D. The first thing I need to do is develop a rate law expression. You say, well, the rate of the reaction is equal to some constant for this system at this temperature, lowercase k, times the things that could affect it. In this case, you have two reactants, A, and it's going to be to some order, and I'm going to multiply that times the concentration of B, and it's also going to be to some order. Your job in these problems is to solve for the order. Now, you say, well, what about C and D? C and D are products. That's after the reaction has taken place. A and B can affect the reaction rate. C and D cannot. Also, please do not forget to include K in your expression, because we can solve later for K, a constant particular to this system at one temperature, one set of conditions. We'll pause momentarily. Looking at number 1 from worksheet 5, Kinetics Rate Laws 1, we see we have a system with hydroiodic acid decomposed into hydrogen and iodine, 2 to 1 to 1 stoic. We've got a series of experiments. HI is my only reactant, so that's the only factor. They didn't tell me what I'm measuring. I could be measuring the disappearance of this, the appearance of that, or the appearance of that, but alright, so they didn't tell me. In my first experiment, they said the concentration of HI is 1 times 10 to the minus 3. This is molarity, moles per liter. And my rate was 3 times 10 to the minus 5. I did another experiment. I took that concentration and I doubled it. And my rate is 1.2 times 10 to the minus 4. And I did another experiment, and now I'm 3 times the concentration. And my rate is 2.7 times 10 to the negative 4. First thing you do, write the rate law expression. You say, all right, well, rate is equal to some lowercase k times the concentration of HI to some order, and that's your job. You need to find that order. Pause momentarily. Okay, so between experiment 1 and 2, I took my concentration of HI and I doubled it. What happened to my rate of reaction? Well, what is 1.2 times 10 to the minus 4 divided by 3 times 10 to the minus 5? Go ahead, plug that into your calculator. You'll see that it's 4. Okay, well, what about experiment 1 to 3? Looks like I tripled my concentration there. What did I do here? What is 2.7 times 10 to the minus 4 divided by 3 times 10 to the minus 5? Go ahead, plug that in. You're going to see that's 9. So doubling my concentration quadrupled my rate. Tripling my concentration increased my rate by a factor of 9. So if 2 gets you 4 and 3 gets you 9, isn't that 2 squared and 3 squared? The order is 2. So my rate law expression is rate equals k times HI squared. The final thing we need to do then is solve it for a value of k. Pick any of your experiments. I'm going to pick the first one. The rate, well, that's 3 times 10 to the minus 5. I'm going to solve it for k. My concentration of HI is 1 times 10 to the minus 3 squared. Divide by 1 times 10 to the minus 3 squared. And you have k. Plug it into your calculator. Be a little bit careful with that, but you should get 30.